You can't open a magazine today or a newspaper or even spend time online without hearing something about genomics this or genomics that or CRISPR this or the human genome. And that's right. There's an incredible life sciences revolution taking place. And there are a series of questions that anchor that revolution. And this is one of the most interesting questions. What will it take to sequence and interpret 1 million human genomes? And it's not a trivial question. You might remember not long ago we were celebrating the completion of the first human genome. In 2003, when those articles came out and the completion of the human genome map, we realized how difficult it was to do. Actually, the completion of the first human genome took over 10 years and around $3 billion. In the last 10 years, the cost, of course, of sequencing has gone down. We introduced last year the first $1,000 genome, and that meant that we could sequence and interpret a human genome for less than $1,000. Now, we're very close approaching an inflection point. And that inflection point is going to turn the curve around into the global consumption of genomic product and services. And we're going to get into that in a second as a way to answer the question that we just posed. Almost every one of our cells, remember, has DNA. Huge amounts of DNA. Actually, it's about 6.4 billion letters in the nucleus of every one of those cells. Now, we know that 99% of our DNA is identical. You might see some differences with people sitting next to you. And those differences are determined by certain changes in DNA. In some cases, a single letter that is changed. For example, in this sequence, ATTCCG, one of those T's might be changed to an A. And that might determine whether you have a predisposition for a condition, a disease, for example, like Alzheimer's or breast cancer, and the person next to you doesn't. But it might also determine that you are immune to certain infections, or it might determine that a particular medicine works for you but doesn't work for the person sitting next to you. How many times have we been to the doctor and the doctor says, well, I'm going to start you on this treatment, and if that doesn't work, then we're going to try something else. Often that is because the doctor doesn't know certain things about your genetic makeup. But if they knew that information, they could actually pinpoint better what medicine or what dose works better for you. In other cases, these changes determine how diet affects us. Some people gain more weight eating certain things and others don't. And often that is determined by their genetic makeup, etc. There's a lot of richness in this genetic information. When we sequence and interpret someone, we create this first, a raw file of all that genetic data. Then we start organizing that file to be able to make sense of it. Eventually we have a file with all of those changes, all of those variants. That is where we can start to see the meaning of what is different between this person and this person. The collection of all of those files, it's pretty chunky. It's about 75 gigabytes per person. And just to put it in perspective, that's like 10 times The Godfather in high definition per person. So enormous amount of data with a lot of richness in there. And we're just starting to scratch the surface. In order to realize the promise of this genomic revolution or this precision medicine revolution, we need to have many genomes sequenced and interpreted. And we're talking millions. And here comes the challenge. Interpretation, first, is still a very manual labor. Every time we have one of those variants, every time we find one of those variants, either we know the meaning of that variant through all the scientific efforts that have happened in the world, or we don't. And if we don't, we need to go and find, can we make a determination whether that variant is a pathogenic variant, it might lead to a disease or not. Today, that is still very manual. We have a team of over 100 people that are bioinformaticians, MDs, PhDs, engineers, whose sole job is to make sure that we interpret and we identify and call those variants properly. 2, data today is very much isolated. You have a scientist in the north of Mexico, a company in Australia, a company in China. One might have 200 genomes here, 5 genomes there, 1,000 genomes here, etc. So it's isolated, it's behind walls, it's organized in many different ways, often using third-party applications, but sometimes they're even their own applications. So, lack of standards. Not only is the data isolated, but it lacks standards to be able to be used as a complement or to be able to compare data from these different places. All of this means that sometimes simple queries might take days. You might want to know, hey, I want to know from all the women between 25 and 55 that have had breast cancer, do they also have these other genetic characteristics? In order to set that query, you need to set the data, you need to identify what are the different databases in the world that might have that information, send requests, see what they're willing to give you, etc., etc., etc. So simple queries often take days. This is not scalable. So where are we going now? We strongly believe that machine learning and artificial intelligence need to sit at the center of how we turn this inflection point. We're strong proponents of open source. Our team has developed the most widely used open source platform called Veritas. More than 5 petabytes of genomic data today are managed through the platform, through the Veritas platform. And institutions like the Sanger Institute or IBM Watson actually use this platform to manage their genomic data. Now, why is this important? Well, let's start with automation. We can't continue to do things in such a manual way as the way we're doing them today. So we're training machines to follow the same rules that experts follow when identifying and calling a variant, whether it's pathogenic or not a pathogenic variant, or we don't know. And these machines are quickly learning how to follow the same rules and be able to do hundreds and thousands of variant calls, not just doing one at a time. Now, in order to do that, we need large amounts of data that are actually standardized, meaning they don't sit between someone's computer and a different spreadsheet and a different tool. You need to be able to compare and ask questions of that data. So, complementary data, standardized data. One of the benefits of a platform like Veritas is that the data can sit wherever it is, right? You might have a scientist that is in England and a scientist and a company in China. They might have the information where they have it, and it doesn't have to be transferred or shared with anybody else. What this platform allows us to do is to ask questions and send those questions out and bring back answers, as opposed to having to ask for data and hope that somebody will share that data with you. So, highly automated, data that is complementary, standards. All of this means that now we can do very complex queries across data that sit all over the world, and it can get answers back in seconds. Now, why are we doing all of this? Well, the reason we're doing this is because we strongly believe in the value of this genetic data as it will start affecting your personal life. The realization of precision medicine, whether it's for prevention or for treatment, diet, lifestyle suggestions, requires this large amount of genetic insights to become a reality. There's also new business models that are emerging from this genomic revolution. Think about what happened with Netflix. At the beginning, you might have paid a subscription to Netflix because you wanted to see a movie that somebody else produced. But today, you might actually pay your subscription for Netflix because you want to see House of Cards. It is content that they have created that responds to a certain insights that they've gathered from all the thousands of viewers that they have. So similar models will start to emerge in the genomic space. New partnerships. Every major food company has approached us and other companies in the genomic revolution to better understand the connections between genetics and food, nutrition. How do you respond to certain foods? Actually, new products that are starting to come up into the marketplace. Cosmetics and beauty, the same. Largest companies in the world in this space are trying to figure out how do we better understand someone's genetic makeup in order to provide custom-made products for that particular genetic makeup. Sports, health and life insurance, you name it. Here's where AI will play a significant role. Nobody wants to interact with their genomic information like if it were a lab test result. Giving you 100 pages with insights, 50 pages with insights is ridiculous. It feels like the 1980s. We need to be able to provide ways for people to engage with the meaningful data from their own genomics, like anything else they do in their life. Just like you ask for the weather on your cell phone, just like you look online for something, just like you want to know where's the closest healthy restaurant, that's how you should be able to interact with your data. One of the things we did last year was, for the first time ever, we connected Alexa, in this case, could have been any other device, to our backend system where we have stored those human genomes. And we actually queried an actual human genome through Alexa with questions like, Alexa, ask Veritas, am I at risk for a certain condition? And she could respond back and say, actually, you are at risk. And in your last blood work, you had some levels elevated. Would you like me to make an appointment with your doctor? Or something about nutrition. And Alexa might suggest certain food options that are better for you than others. And that is how we want, and we strongly believe that consumers should be able to interact with their genomic data. That's what we're building. Now, this could be Alexa, it could be your iPhone, it could be Google Home. This should be device agnostic, and it should be platform agnostic. Now, you might remember in 2007, when the iPhone was first introduced, one of the questions that kept coming up in the press was, well, how many people are actually going to buy this new device? And 1 year later, by the fourth quarter of 2008, about 8 million iPhones had been sold. In the first quarter of this year, 2017, close to 80 million iPhones were sold. So I want to leave you with a quote from our CEO. We have a path to sequence and interpret 1 million genomes. But the question that we should all be asking ourselves is, how are we going to sequence and interpret hundreds of millions of genomes? And that's how we realize the value of this genomic revolution. And we're very excited to be driving that.